one of the speakers that I'm so proud to introduce to you today, right now, to kickstart the afternoon section, is Brian McKenna. He's the head of products at Mina Foundation. Mina Foundation is a public benefits corporation serving the Mina protocol, the world's lightest blockchain. So Brian is championing product development for Mina protocol, the focus of which is building a lightweight and also secure blockchain. Now he will speak to us about building the privacy and security layer for Web3 with zero knowledge. So please welcome Brian.
Testing? Sounds good? Okay. Hi everyone. Thank you for coming to the talk, especially to those of you who have just had lunch. Hopefully we'll make it through this together. My name is Brian McKenna. I'm head of product at Mina Foundation. And Mina Foundation exists to serve and empower the Mina community and the Mina protocol itself. Today I'm going to speak about privacy and security for Web3 and with a special focus on zero-knowledge smart contracts. And we're going to get into a lot about what they are during the presentation. So first, I'm going to give an overview or a refresher on Mina protocol for those who know it and for those who would like to hear an update. We're going to zoom out a little bit and we're going to talk about the current state of privacy today as it relates to Web 2 and Web 3. And then we're going to get into what are Mina smart contracts, zero knowledge applications, or ZK apps as we like to call them. And then we're going to go through a worked example of a ZK app, and we're going to see how that ZK app can be used cross-chain by another L1 in a fully trustless way so that those L1s can access the zero knowledge computation properties of Mina protocol. And then we're going to talk about what's happening next and what the latest releases on the roadmap are. Okay, so Mina was incubated by a team called O1 Labs, and they were working on it since 2017, and mainnet launched in March 2020. Mina is a layer 1 blockchain, and we like to call Mina the lightest blockchain in the world. And I'll get into what that means later on. And of particular interest is zero knowledge proofs. And Mina has zero knowledge proofs built natively into the protocol. And they're used to achieve this lightweight property. And also we're going to talk about how they're useful for ZK apps and why they're important for smart contracts as well. Okay, so before I get into ZK apps, let's talk a little bit about how to think about Mina versus other blockchains, other layer 1s. So other blockchains, they have state and blocks, and those blockchains grow in size over time. So as new transactions are created and blocks committed to the network, those blocks are stored by every full node on the network. And the storage footprint of all these blocks grows in size over time as the network moves forward. So an example that I've given here is 400 gigabytes right now is the data footprint for a Bitcoin full node. And Ethereum is about 1 terabyte currently. So in contrast to that, Mina is what we call a fixed size, succinct blockchain. Fixed size in that the data footprint for a node remains constant over time, forever, and succinct in that this data footprint is ultra small at 22 kilobytes. So how do we achieve this 22 kilobyte footprint? So instead of every node on the chain storing every block and all of the blockchain states since Genesis, instead, Mina stores a zero knowledge proof which represents the blockchain. Now, this zero knowledge proof says 3 things, and these three things all round up to about 22 kilobytes of data. So the first thing it says is that there exists a blockchain, Mina protocol. The second thing is it says, here is a proof that verifies the entire chain state since Genesis. And third, it says, here is a proof of the Merkle root of the current state of the ledger. And with these three things, a node can sync with the network ultra fast, and people can participate as a full node with very, very lightweight computers, right, or devices. So think about browsers and cell phones and this type of thing. And this has a good impact on decentralization because of the low hardware requirements and the low barrier to entry, then many people who might not want to run like big infrastructure or equipment to participate as a full node can participate in Mina. So just to talk again about what kind of benefits this succinct blockchain brings, every node can participate as a full node with only 22 kilobytes. There's no cap on the number of validators. And as we said, nodes don't need to store the entire history of the chain to participate as a full node. So in practice, what this means is that somebody can verify the entire Mina blockchain in a matter of seconds and join the network super fast and keep up with the network super fast. Another really important thing is that because of the lightweight properties, there's no need to trust and use a third-party operator to access the network for you. So the nodes can access the network directly without having to use an intermediary. And like think of an example here as being the way we use Infura to talk to Ethereum and things like this. Now, because we have ZK snarks built natively into the protocol, we can now think about starting to do other cool things with them. Particularly zero-knowledge computation for smart contracts. And this has particular benefits for efficiency and privacy, which we're going to get to later. All right, let's zoom out a little bit and talk about privacy as it relates to Web 2 and Web 3. So we all know that ZK is good for scaling, right? That's like the particular use case that it's most famous for now, and it's the use case which kind of needs to be urgently addressed in regards to scaling blockchains, particularly for layer 2 protocols. But zero-knowledge proofs are also really good for privacy and computing things without revealing what the things are that you're computing over. But what is privacy and why is it important? Well, like privacy is well documented in many countries and like constitutions and regulations around the world, and it's even documented in the UN Declaration of Human Rights as being a fundamental human right. At its core, this fundamental right is related to privacy over your identity and your actions. And in Web 3, we can define privacy as the ability to decide what you want to share and who you want to share it to. So today in Web 2, we don't really have these properties. We don't really have the option to decide what we want to share and who we want to share it with, because the data is controlled by third parties in centralized servers who have custody over our data, and we really don't have much control over it, what happens with it, how secure it is, and what type of things it might be used for. The transition from Web 2 to Web 3 should be defined by giving control back to the users in a decentralized way, where those users can have control over the data locally on their device or their machine, and they control when to release the data and who to share it with. And importantly, they have custody of their own data, so it's safe and secure in that way, according to how they want to manage it. So let's get into Mina smart contracts, zero knowledge proofs, or ZK apps. Before we get into really what ZK apps are, let's look at most dApps today and form a way to think about ZK apps versus how most apps today work. So in this example, as an Ethereum end user, I'm going to send a transaction to the network with some state update. That transaction is going to have some instructions in a payload, and that payload is going to get delivered to every node on the Ethereum network. There, every node will execute the payload and instructions, and if it's a good update, then the transaction will be settled, and the new state will be committed to the application. Now, there are a couple of things to point out here in relation to how Mina works differently. So the first thing is efficiency. It's not incredibly efficient for every node on the network to run every transaction. Moreover, every new node that joins the network needs to re-execute every single transaction that's been created on the network since Genesis. Second is privacy. So any data or any information which was used in the application update from the end user gets executed by nodes which the user doesn't know and the user doesn't trust. And all of this data is clearly visible in a transparent way on the chain. In contrast, in Mina, the execution happens off-chain. So we can see a similar example here. The application update happens on the user's machine or device, and what gets sent to the Mina nodes is a zero-knowledge proof of the correctness of the computation and the new state of the world that those instructions kind of like refer to. So back to the benefits of this. So user privacy through zero knowledge. We can see here that the execution happens off-chain. Therefore, any particular data that was used in the application update from the user stays on the user's device or machine. The only thing that gets sent to the network is a zero knowledge proof that the updates were executed correctly. So we can see here now that we can compute over data which we don't want to release to everybody on the network. This might be personal identifiable information. It might be business logic according to your business, or just general things that you don't want everybody in the world to know about. The other thing is unlimited off-chain execution. So just back to the example, we can see that the execution happens off-chain. So we're not bound by the size of the execution which has taken place. We know that on normal smart contract systems, the gas cost is proportional to the size of the computation that you want to do. Well, in this case, the size of the computation doesn't really matter, because in the end, on Mina, the gas cost is proportional only to the number of proofs which get sent to the network. So we have an efficient and gas predictable system here. And just more about efficiency. So the instructions for the state update for the application don't need to get re-executed by every node on the network. The computation has already happened off-chain, and the only thing that gets sent to the nodes is the zero knowledge proof of the computation. So it's very efficient in that way. And also, it doesn't matter like the complexity or simplicity of the computation. A super complex computation will only result in the same zero knowledge proof being sent to the network as a super simple one. So it's practical here to compute over like complex, large data sets without revealing what those data sets are and without impacting the efficiency of the nodes on the network. So, ZK app consists of two parts: the smart contract and the UI. The smart contract itself is written in TypeScript using our library Snarky.js. We chose TypeScript because it's a very common and accessible programming language. And it's very well known, and there's lots of really cool tooling, and it's just an easy thing for people to develop with. The zero-knowledge cryptography itself is abstracted away from the developer. So the developer doesn't need to understand the really complicated mathematical cryptography that lies underneath. They just need to understand how the abstractions work to be able to build their application using Snarky.js. The UI itself can also be written in TypeScript, luckily, and the developer can use one repository via NPM and upload their whole application into the browser. So how does the smart contract work? What are the things that a smart contract compiles down into? So we spoke about off-chain execution. So we have the prover function, which runs locally on the user's machine and generates a zero-knowledge proof of execution for what it was supposed to execute. So in the sense that the prover will do exactly what you tell it to do, and if it does so correctly, then the zero-knowledge proof will likely pass verification by the verification key, which is stored on Mina. And the verification key is where the business logic of the smart contract exists, and any constraints or any bounds or anything like that that the developer wants to build into their application. So when you deploy a verification key to Mina, there gets created a ZK app account. And the only way that this ZK app, the state of this ZK app account can be updated is if it receives a valid zero-knowledge proof from the prover function, which lives on the client's machine. So as I do the end side, I do my computation, I send the ZKP to Mina. The state of the contract will only update if the verifier function on Mina sees that it's a valid zero-knowledge proof according to the business logic and constraints in the smart contract. The nodes will reject a zero-knowledge proof if they like fail verification. For example, if somebody was trying to run a malicious computation instead of really what the smart contract is kind of built to receive. Just a little bit about Snarky.js, which I mentioned at the start. This is our zero-knowledge programming library, and the surface language for this is TypeScript. It uses all open existing technologies, so you can use your use your tooling that you're familiar with if you're a TypeScript developer. And we think it's a very low barrier to entry for developers to start building with zero knowledge. So what can you build with this? Well, it's almost like when smart contracts were created in 2016. We don't really know yet until builders come along and experiment and use their innovation and creativity. But some nice examples to run through are private DAO voting, where you want to build your vote locally and send proof of your vote to Mina without revealing your identity or which direction you voted. Real-world financial data. So DeFi has a problem because it can't check people's credit history or identity. So therefore, DeFi loan and borrowing applications have to over-collateralize for borrowers. Well, we can send proof of KYC or proof of credit worthiness to DeFi, and there's no need now for the borrower to have that over-collateralization. Safe interoperability of private enterprise data with public smart contracts. So imagine two enterprises want to collaborate over some data sets that they each have in-house. Well, they don't really want to share what's in those data sets, like their customer information or business logic or whatever, but they do want to prove certain things about what lives in those data sets. Well, all this will happen off-chain, so only the proof of what they care about will get sent to the chain. And in this way, two enterprises can collaborate in a public blockchain environment without sharing their data. It's very easy to spin up ZK rollups on Mina, which is really useful for gaming in particular. And this is because of the recursive nature of our proof system. We can also anonymize on-chain information to prove things over various account balances or NFT ownership or anything that happens on chain really can be proven without revealing the user's account, for example, or their balance in a lot of cases. And another thing which could be built is a private payment system a la Zcash. Okay, so we've spoken about ZK apps. If we wanted to use ZK apps in a cross-chain environment, how could we do this? And why would we want to do it? So firstly, ZK apps could be really useful to other L1s which don't have this zero-knowledge cryptography built natively into their protocol. So because Mina specializes in zero-knowledge and zero-knowledge smart contracts, we want to create a good way for other L1s to be able to access ZKPs in a trustless way cross-chain, so that developers on those L1s can enhance their applications to use some of the privacy and trust features that ZK apps give. Also, in particular on Ethereum, running ZKPs have a very, very high gas cost on the EVM. So, and it's worth noting that this product, which we call ZK Bridge, is being built right now. There is a demo available at the website of Nil Foundation, who are the developers, and it's being built under a grant from the Ethereum Foundation and the Mina Foundation jointly. So, to do this cross-chain bridging, we want to leverage Mina's succinctness properties to allow the EVM to verify the state of Mina right inside the EVM. So we will verify Mina inside of the EVM, as I said, in a canonical Mina smart contract that lives in the EVM. So anyone can update the Mina contract on EVM, which means that we're going to grab the Mina state from a Mina node, upload that into Ethereum, and then the EVM contract will check a couple of things. So it'll check that the upload contains the strongest state of Mina and the Merkle root of its ledger. And what this now means is that right in the EVM, or indeed any EVM-based chain, a developer can access the Mina state just by calling the canonical Mina smart contract in the EVM. So if they have a zero-knowledge proof of something which lives on Mina, that can now be accessed by Ethereum developers or EVM-based developers on other chains. And it can be accessed by many applications. It's not a one-to-one thing. So, 10, 20 applications could access the same zero-knowledge proof on Mina if it was useful for their application. So let's run through a worked example that demonstrates a couple of things. So ZK apps and using ZK apps in a cross-chain way. So let's say we want to create a DAO, and membership of that DAO is predicated on proof of attendance at BUIDL Vietnam. So the user will create a ZK app account on Mina with the verification key was at BUIDL. The user will submit a proof of identity that matches their pass, and they'll update the data field in the ZK app to be their Ethereum public key. So the Mina bridge contract will get updated with the latest Mina state, and the Mina state will now have the Mina state on Ethereum will now have a proof, a zero-knowledge proof of two things. So the identity of the attendee and some record that they actually were physically at the event. But only a proof, so we don't see their identity and we don't see their ticket number or whatever it is that they've used to prove attendance. So the DAO contract on Ethereum can now call the canonical Mina state contract and check out what's there. So the Ethereum DAO contract will check the Merkle path from Mina to the Mina state. It will check that the Mina account has the right verification key, and it will check that the user with their Ethereum public key signed against the Mina ZK app. And once all this is achieved, the user on Ethereum who's been identified as being at the conference gets added to the new DAO on Ethereum. And we haven't revealed their identity, and we haven't revealed their ticket number and all of these things. And then it's a really nice way to prove conference attendance. And now the DAO can proceed, trusting that everybody in that DAO was actually physically at the conference and do whatever jobs it's supposed to do after that. So that brings me to the end of my talk. Thank you to everybody for your time and attention. A really good way to get involved is to go to Discord, and in particular if you're a developer, ZK Apps Developers channel. The docs are a really good place to start also. And an update on the roadmap. So we've just launched the testnet, which is the ZK Apps upgrade to Mina. And that's going to be the first major hard fork that we've had on the protocol. And it's really, really a big thing for us. That testnet is in a beta mode right now, and we'll be moving into an incentivized testnet, likely next month, with the mainnet hard fork to follow soon after. Another thing to note as well is that we're having a developer meetup in the city tomorrow at 3 p.m. And we'll share some of the details about that in the conference telegram. But that's all from me. Thank you, everyone, and see you later.
Thank you, Brian. Thank you so much for your sharing.